So in this video, I'm going to continue with CC7 and we're going to look at polymers. Because this is CC7, this comes up on paper 1 and on paper 2. In the previous video, we looked at simple molecules and we saw that molecules was when you had a known number of atoms that were covalently bonded together. Because you only had covalent bonds, those atoms were always non-metals. All of the molecules we looked at in the previous video were quite small. In this video, we're going to look at simple molecules, polymers, that are larger. Okay, so they are still simple molecules, they're just larger than what we looked at before. Polymers are long chains made up of small units called monomers. And the easiest way to show this is just to show you an example straight away. Is a few different examples of the small monomer ethene. So ethene is a simple molecule, okay? I know that because I've only got non-metals, carbon and hydrogen, so they are covalently bonded, and I've got a known number of atoms, 2 carbons and 4 hydrogens. Ethene is a small, simple molecule, and I call it a monomer. If I take lots of ethene molecules and join them all up together, I can form a chain called a polymer. So I have just drawn out 5 ethene molecules for the sake of time, but I could draw many, many more. And if I join all of these ethene monomers together, I will form what is called a polymer. Now, if you just look at what I've drawn here, if I were to try and just attach these molecules, together by just joining them up like so, what you will hopefully notice is by doing that, by joining all of these molecules together, that carbon will end up with 1, 2, 3, 4, 5 bonds when it can only have 4. So I can't just join all of those ethene molecules together because carbon will have too many bonds. So instead, to join all of those ethene molecules together, I will need to lose something. And what I lose is the double bond. So I've drawn it out below here. And it's the same thing as what I drew above, except I don't have any double bonds between the carbons. Now each carbon only has 4 bonds around it, and I'm able to join all of those individual ethene molecules into one long chain called a polymer. Okay, so your small individual subunits are called monomers, and in this join all of those monomers together, I get a long chain, which I called a polymer. And the word polymer just means many. So I would call this polymer polyethene, which means I've got many ethenes all joined together, and I form this long chain. Now, in reality, even though this chain looks quite long on my page, in chemistry terms, this would be a very short chain. When I'm talking about long chains, you're talking about, even like 100, 200 carbon atoms in a chain. And because that would be incredibly tedious to draw out in full, rather than drawing these chains in full, we use this notation here, where you take your carbons and you take your hydrogens, so you draw a small unit of the polymer, okay, usually just 2 carbons, and then you put it in a bracket, and then you use the letter N. And N stands for any number. So if that number there was 5, that would tell me that I've got 5 of these units, which is exactly what I have above. Okay, so each unit contains 2 carbons. If I had 5 of these units, I would have 10 carbons, which is what I've drawn above. Okay, 5 units is manageable to draw, but if this number here was 100, then I would have 100 of these units, which means I would need to draw 200 carbons because there's 2 carbons in each unit, and that would be incredibly tedious to draw. So typically we don't draw polymers out in full, okay? We just put a small section of the polymer with 2 carbons into a bracket and use the letter N, which tells you that, N will be a number and it will tell you how many units you would draw. You will also notice that I've got 2 bonds here that just extend outwards. That's to tell me that I could grow the chain in this direction to the right, or I could continue going the chain in this direction to the left. And you'll see I've used those same bonds in the polymer above. It just represents that the chain can keep going in each direction, which is what a polymer is. It is a long chain, okay? So even if I did have N equals 100 and I had 200 carbons, okay, it's still a known number of atoms, okay? They're still all covalently bonded because I've got carbon and hydrogen, so they're all covalently bonded. Even though a polymer is much bigger than what we looked at in the last video, polymers do still count as simple molecules, okay? So monomers, the small units, they're simple molecules, but even when you join all of those monomers together and form a polymer, polymers are simple molecules, okay? So in the last video, we looked at the properties of simple molecules, and we saw that simple molecules do not conduct electricity. And the reason they don't is because they don't have free moving charged particles. Polymers are simple molecules. So if you are asked, do polymers conduct electricity? You will say no. They are simple molecules and they have no free moving charged particles to carry current. The other thing we learned about simple molecules is that they have low melting and boiling points. And the reason they've got low melting down here, they've got low, I'm going to write MP for melting point and BP for boiling point. They have low melting and boiling points because they had weak intermolecular forces. And that word intermolecular literally means between molecules. So the forces between molecules are very weak, so they don't require much energy to overcome. Polymers, okay, I know they're longer, but they are still simple molecules. So polymers have weak intermolecular forces. However, because polymers are so much longer, notice that I said their intermolecular forces are stronger. I didn't say they were strong. So if I've written out an answer here, okay, so polymers are simple molecules, but they are often solid at room temperature, whereas previously we saw that simple molecules were liquids or gases. The reason they can be solid at room temperature is because they have those long chains, they have stronger intermolecular forces than small molecules, okay? It's not correct to say they have strong intermolecular forces. Intermolecular forces are never strong, okay? But because they're long chains, they're just stronger compared to other simple molecules. And the reason they're stronger, and you won't be asked to explain this, but the reason they're stronger is if I've just drawn a shape here, but quite a small shape, okay? And if you can imagine, if I've got this relatively small shape, and these molecules are attracted to each other, okay? So I've drawn there in blue, these molecules are attracted to each other, and we're going to call these the intermolecular forces. If I've got a really long chain, you'll notice that I am able to draw a lot more intermolecular forces between the chains. And because I can draw a lot more intermolecular forces, overall those intermolecular forces are stronger, okay? So polymers are simple molecules, but they are often solid at room temperature because they've got these long chains, they've got stronger intermolecular forces than a small molecule, therefore they require more energy to overcome and are often solid at room temperature, whereas your other small simple molecules are typically liquids or gases. We'll look now at some typical exam questions in polymers, and to be honest, there really aren't that many, okay? So here's one that says, explain why polymers are normally solids at room temperature, and it's for 3 marks, okay? So you would specify that they are large molecules or long chains. Because they're larger, they've got stronger intermolecular forces than small molecules, okay? It's really important there that you're saying stronger and you're not saying that the intermolecular forces are strong. It's just that they're stronger than small molecules. And because overcome these forces. So anytime you're asked about something being a solid, a liquid or a gas, melting or boiling point, any of those type of questions, please remember to use the word energy. More energy is needed to overcome these forces. The other typical questions, they often give this to you as a multiple choice question, but they'll draw this little structure below and they'll ask you what it is. Anytime you see those brackets and that little N, that represents a polymer. Okay, so that's a typical question. What structure? It's a polymer. If you see the brackets and the N, it's going to be a polymer. The other thing they can do is You don't need to actually learn these properties off by heart, but they can give you properties and they can give you uses, and they can ask you to link the property to the use. So polymers are used in plastics. So you've got lots of different types of plastic. You've got the plastic in plastic bags, which is really flimsy and flexible. And then, have the tougher plastic, that you can use to make containers. And different plastics are made out of different polymers, so different chains of carbon atoms. And different polymers have different properties, so have different uses. So in this question here, they've given you a table that has properties and uses, and then they ask you questions about it. So they go, suggest why PFTE is used as a container to store laboratory substances. So I've got PFTE here, and it does tell you that it's used as a container for laboratory substances. Then you need to look at its properties and see which property makes it appropriate for the use of a laboratory container. Okay, the fact that it's slippery, that doesn't help storing lab chemicals, but the fact that it's chemically unreactive does. This means that you can put a chemical into PFTE as a container, and the it is storing. So the fact that it's chemically unreactive is important. The next one, why is polythene used to make carrier bags? Okay, so if you look at your table, you'll find polythene, and you'll see that it is indeed used to make carrier bags. What property makes it appropriate for a carrier bag? Well, you want a carrier bag to be flexible, and you want to make a carrier bag to be cheap. Okay, carrier bags are disposable. You don't want them to be expensive to make. Okay, so they're flexible and they're cheap. That's why they're used for carrier bags. PVCE is an electrical insulator. Explain why. So if something is an insulator, that's the opposite of a conductor. Okay, so if it's a good insulator, it's a bad conductor. So they're asking you, why is PVC a bad conductor? We've seen this already. If it's a bad conductor, if it does not conduct electricity, it's because it does not have free moving charged particles and so cannot carry current. And the last one here, polymers are simple molecules, yet they are typically solids at room temperatures. Explain why they are solids at room temperatures. It's what we've seen before. They are long chains, so they are larger molecules. They have stronger intermolecular forces than small molecules. Therefore, they require more energy to overcome. Okay, that's all you would need to say. And that's pretty much all they're going to ask you about polymers.